Hello everyone, my name is Nidhi Chauhan and I am assistant professor in Gyan Vihar School of Pharmacy that is a part of your Suresh Gyan Vihar University, Jaipur. So today we are going to discuss this topic that is your cycloalkanes. That comes in your pharmaceutical organic chemistry second in your fifth unit and in this today's learning objective is. So here we are going to study about the Bayer strain theory, and also we are going to study about the orbital picture of this angle strain, and also we are going to learn about the Colson and Moffitt modification. And student outcome is that they will be going to know about the Bayer strain theory and its limitation. That what is the Bayer strain theory? What the scientist Bayer or Bayer, the scientist Bayer has given his theory about this cycloalkane, and what are the limitations that is not applied to all the cycloalkanes compound molecules, and they will be going to know about the angle strain, that what is the angle strain and what is this picture of the orbital picture of this angle strain. And they will also going to know about the Colson Moffitt modification, means the scientist Colson and Moffitt modification, what modification they have given in the cycloalkane theory. So here, this is the learning objective and the student outcome. Let's start the topic. So the Bayer-Stein theory, first of all, the Bayer-Stein theory. So the Bayer postulated that any deviation of bond angle from the normal tetrahedral value would impose a condition of internal strain on the ring. So here the Bayer postulated that if there is any deviation in the bond angle and from the normal tetrahedral value would impose a condition of internal strain on the ring, means that you know that these alkanes are having a tetrahedral structure. So here, if there is any deviation in that tetrahedral value, and which is due to this internal strain on the ring, and which imposes, if there is any deviation of bond angle from this tetrahedral value, then they will apply or they would impose a condition on this internal strain on the ring. So the bond angle is of 109 degree 28, or you can say 109.5 degree. That is for the carbon atom in tetrahedral geometry, means the alkanes which are having in a which are in the this tetrahedral geometry. This alkane means this methane molecule which shows the bond angle is on 109.5 degree. So the Bayer observed different bond angle for different cycloalkane, also observed some different properties and stability. So here the scientists that observed that there are different bond angle for different cycloalkane, means it shows that the alkanes which are having the tetrahedral structure, means they are having the bond angle 109.5 degree in all the alkane molecules. But in case of this cycloalkanes, there is different bond angle for different cycloalkane, and they are having this different properties, and due to that different bond angle there are different properties and stability also in this cycloalkanes. So this was observed by the scientist Bayer. So on this basis, he proposed more angle strain theory. So on the basis of this theory, which he observed that the different due to the different bond angle for different cycloalkane, they observe different properties and stability. So on this basis, they are proposed angle strain theory. So here the theory explains the reactivity and stability of the cycloalkane. Means this theory, this Bayer's chain theory, is explaining the reactivity. Means what is the reactivity and what is the stability of the cycloalkane. So Bayer proposed that the optimum overlap of atomic orbital is achieved for bond angle of 109.5 degree. In short, it is effective, and optimum overlap of atomic orbital produces maximum bond strength and stable molecules. So the Bayer proposed that the optimum overlapping of orbital is achieved for angle. Means if there is a overlapping of atomic orbital is achieved, then there is a bond angle is 109.5 degree. It is effective and optimum overlap. Means this optimum overlapping of the orbital atomic orbital is effective and it is optimum, and it produces maximum bond length and stable molecule. Means this atomic orbital is producing the maximum bond length and the stable molecule. If bond angle deviate from the ideal, then ring produce strain. If this bond angle deviate from the ideal, means the bond angle, if the ideal angle or the value is deviated, then the ring produces strain. Then the higher the strain, the higher the instability. It means that if there is any strain on the in this ring, then there is a higher instability in this cycloalkanes. So higher strain produces increased reactivity and increased heat of combustion. So if there is a higher strain, then there is a higher instability, but there is a higher reactivity also, and there is an increase of heat of combustion also. So Bayer proposed any deviation of bond angle from ideal bond angle will produce a strain in molecule. Higher the deviation, lesser the instability. So here the brain Bayer proposed a theory. In this theory, he noted that if there is any deviation in the bond angle, deviation in the bond angle from the ideal bond angle, means the ideal bond angle value is your 109.5 degrees, that is for the cycloalkane. And if there is any deviation from this bond angle, then there is a strain that is produced in the cycloalkane or the cycloalkane molecule. So if there is a higher the strain, if there is any higher deviation, if the deviation is higher, then the instability is lesser, then the instability is your lesser. Next, again, I'm telling you that the Bayer strain theory is postulated that any deviation of bond angle from the normal tetrahedral value would impose a condition of internal strain on the ring. Means Bayer postulated, this is a scientist name, this strain theory is given by the this strain theory is given by the scientist, that is your Bayer. And the Bayer postulated, means he postulated that any deviation in the bond angle, means any deviation of the bond angle from the normal tetrahedral value would impose a condition of internal strain on the ring. If the ring, means here the cycloalkanes, cyclopropene, cyclobutane, cyclohexane, cycloheptane, if they are having, that ring is having any a deviation in the bond angle, means here bond angle, ideal bond angle is taken as the tetrahedral bond angle value. So the tetrahedral value is your 109.25 degree and 109.5 degree. And if there is any strain, if there is any deviation in that bond angle, then that will impose a condition of internal strain, that will apply a strain on the ring. So the bond angle is 109.5 degree for carbon atom in tetrahedral geometry. Means that the alkenes which are in the tetrahedral geometry, they are having the bond angle that is your 109.5 degrees. So this bond angle is applied to all the alkane molecules, and in the case of cycloalkane, if there is any deviation in this bond angle, means in this 109.5 degree angle, then there is any strain that will apply a strain on the ring. Next is your Bayer observed different bond angle for different cycloalkane and also observed some different properties and stability. So here Bayer observed different bond angle for different cycloalkane and also observed some different properties and stability. So if Bayer on the different cycloalkane, means on different cycloalkane, means here cyclopropane, cyclobutane, cyclohexane. So on that, he observed that there are different bond angle on these different cycloalkane, and they are showing if their bond angle is different, then their his properties and the stability is also different. So he observed that this Bayer observed this, that if he is having a different bond angle, then he in different cycloalkane, then he is then there is a then the different cycloalkane are having the different properties and the different stability. On this basis, he proposed angle strain theory. So on this basis means different bond angle for different cycloalkane and different properties. They are showing different properties and stability. On this basis, he proposed a angle strain theory. So in this theory, He explained the reactivity and stability of cycloalkane. So in this theory, means in this Bayer angle strain theory, he explained the reactivity as well as the stability of the cycloalkane. So the Bayer proposed that the optimum overlap of atomic orbital is achieved for bond angle of 109.5 degrees. So here the Bayer proposed a theory that the atomic orbital overlapping of atomic orbital is achieved in the bond angle of your 109.5 degrees. That is for the tetrahedral geometry. And in short, it is effective. This bond angle, this optimum overlapping of atomic orbital is effective, and this bond angle, that is your 109.5 degree, is effective and optimum overlap of or atomic orbital, and it is producing maximum bond length and stable molecule. And it is producing maximum bond length and stable molecules. So due to this optimum overlapping of atomic orbital and this it is producing a maximum bond length and the stable molecule. If bond angle deviates from the ideal, then ring produces strain. Means if the bond angle deviates from the ideal bond angle, that is your 109.5 degree, then the angle will produce a strain. Then the cycloalkane or the ring, you can say, it will produces a strain. So higher the strain, higher the instability. Means if the strain is higher, then the instability is also higher. So higher strain produces increased reactivity and increases heat of combustion. So this higher strain is producing increased reactivity and increased heat of combustion. So Bayer proposed that due to this higher strain, there is a higher instability and there is a higher reactivity, as well as your heat of combustion is also increased. So Bayer proposed a theory. In this theory, he said that that any deviation, means if there is any deviation in the bond angle, that is from the ideal bond angle, that is a 109.5 degree, then there will produce a strain in the ring. Means there is a strain in the ring or in the molecule, and due to that there is a higher deviation. If there is a higher deviation, then there is a lesser instability there. Next is your Bayer theory is based upon some assumptions as follows: that all ring systems are planar. So the Bayer theory that he has given, the angle strain theory, it is based on some assumptions as follows. The first assumption is that all ring angle are planar. So the ring angle all ring systems are planar, means the ring system means the ring all the ring system means the all cycloalkane should be planar, and deviation from normal tetrahedral ring angles result into instable cycloalkane. So here all ring system should be planar, and if there is any deviation in the ring system from the ideal tetrahedral angle, then it will result in the unstable cycloalkane. Next is the larger the ring system involves negative strain, hence do not exist. So if the ring system is larger, then it involves negative strain and which does not do not exist. So here, if the ring system is larger, okay, then there is a negative strain, hence do not exist. So here, there will be no strain that will exist on that ring system. So the bond angle in cycloalkane and higher cycloalkane means cyclohexane and higher cycloalkanes means heptane, cycloheptane, octane, nonane, decane. So in that ring system are not larger than 1095 degree, because the carbon ring of those compounds are not planar, but they are puckered, means wrinkled. So here the bond angle in cyclohexane and higher cycloalkanes are not larger than 109.5 degree, means their bond angle is not larger than the 109.5 degree, or you can say that they are not larger than the ideal bond angle. So due to the carbon angles because of the carbon ring of those compounds, because the carbon rings of those compounds are not planar, means not flat, but they are wrinkled, or you can say puckered. So here you can see that all carbon atoms are sp3 hybridized, except expected bond angle is 109.5 degree. So here the three examples are given: cyclopropane, cyclobutane, cyclohexane. 1, 2, 3, 4, 5. Cyclohexane. So sorry, cyclopentane. So this is your cyclopentane. This is your cyclobutane. This is your cyclopropane. So here all the carbon atoms, all the carbon are having the sp3 hybridization, all are having the sp3 hybridization, and the angle expected angle is your 109.5 degree. And in this case the deviation is your 109.5 degree. That here you can calculate the deviation. So in this case, in the cyclopropane case, the deviation is your, you can minus 109. This is the ideal bond angle. And this cyclopropane is having the bond angle that is a 60 degree. All the three carbon is having a 60-degree bond angle. So here you will calculate it that the deviation is 49.5 degree, and in case of cyclobutane the deviation is a 19.5 degree, because the angle shown by the cyclobutane carbon is a 90 degree, and in case of cyclopropentane the deviation is a 1.5 degree. So this deviation in case of cyclobutane, that is exists as a puckered wing conformation, means a wrinkled wing conformation, and in this the deviation is very small. So here it exists as open envelope conformation. So it is existing as an open envelope conformation. So in this Bayer theory is based upon some of the assumptions as follows: that all the ring that are in the cycloalkane, they should be planar. Secondly, the deviation from normal tetrahedral angle result into unstable cycloalkane. So here, if there is a deviation in this normal tetrahedral angle, then it causes the instability cycloalkanes. So here, if there is any deviation in the normal tetrahedral angle, that is your one ideal angle, that is your 109.5 degree, then it causes the unstable cycloalkane. So it causes the unstable cycloalkanes. So secondly, the larger ring system involves negative strain, hence do not exist. So if there is a larger ring angle, then then it causes the negative strain, and that does not exist. Means that there is no strain on that larger ring system. Next is the bond angle in cyclohexane and higher cycloalkane are larger than 109.5 degree, because the carbon ring of those compounds are not planar, but they are puckered or wrinkled. So here the bond angle in this cyclohexane and higher alkane, for example, is your cycloheptane, cyclooctane, cyclononane, etc. These are not having a larger bond angle than this 109.5 degree. So these carbon ring of those compounds, these carbon rings are present in that cycloalkanes, they are not planar, means they are flat, and they are puckered or the wrinkled. So the carbons that are present in this sp3 carbon that are present in this ring or in this cycloalkanes, these are all sp3 hybridized. So here the expected bond angle is your 109.5, that is your ideal bond angle, and the deviation in the cycloalkane is your 109.5 degree minus 60 degree equals to 49.5 degree. So in case of cyclopropane, the angle in the carbon atom, the bond angle in the cyclopropane is your 60 degree. So the deviation in this is 49.5 degree. Next, in the cyclobutane. So in case of cyclobutane, the deviation in this cyclobutane is 19.5 degree. And in this, the 90 degree angle is shown by all the carbon atoms that are present in this ring, in this cyclobutane ring. So the deviation is 109.5 degree minus 90 degree equals to 19.5. So the deviation in this cyclobutane is 19.5. As you can see that this is a smaller ring. So it is having a much larger difference deviation. Here differences large. And here, in case of the cyclobutane, here the deviation is 19.5. So from this to this, there is a smaller deviation. So this cyclobutane that is exists as puckered or wing conformation, and this deviation 109.5 degree minus in this case of cyclopentane, deviation is 109.5 degree minus 108 equals to 1.5. So from here to here, you can see that the larger their ring system, the negative strain they exist, but they do not exist any strain. So this exists as an open envelope conformation. Next is your C. In this case, these assumptions are helpful to understand instability of cycloalkane ring system, and the ring of cyclopropane in is triangle. All the three angles are of 60 degree in place of 109.5, and the normal bond angle for carbon atom to adjust them into triangle ring system. So here these assumptions are helpful. So here these assumptions, which I have told you that there are three assumptions in case of this Bayer string theory, and these assumptions are helpful to understand the instability that is present in this cycloalkane ring system, and the ring system, and the ring of cyclopropane, and the ring of cyclopropane is triangle. So this cyclopropane is of triangle shape. So all the three angles are 60 degrees. All the three ring systems that are present in this carbon in this cyclopropane are the 60 degree angle, and 60 degree in place of this 109.5 degree. So here normal bond angle for carbon atom to adjust them into triangle ring system. So here the normal bond angle. So there the normal bond angle for carbon atom to adjust them into triangle ring system. So here the all the three angles that are in the cyclopropane are of 60 degree in place of your 109.5 degree. So here in same manner cyclobutane. So here you can see the cyclobutane is having a square shape. So in the square shape the bond angle is 90 degree. So in place of your 109.5 degree, the normal bond angle for carbon atom, this 109.5 degree is the normal bond angle, or you can say the ideal bond angle for the carbon atom. And here this we have to adjust them into the square ring system. So if we are adjusting, then it will be show this structure. So in case of cyclopropane, you can see that this is 49 degree deviation is coming. So here the ring should be like this. And in the case of cyclobutane, this ring should be like this. And the deviation for cyclopropane and cyclobutane ring system, then normal tetrahedral angle will produce strain in ring. The ring strain will make them unstable as compared to molecules having tetrahedral bond angle. So in the case of the cyclopropane and cyclobutane ring system, the deviation from the normal tetrahedral angle that produces strain in the ring. So here there is a strain in both of this ring because there is a deviation in this bond angle. So here the ring system will make them unstable as compared to molecule having tetrahedral bond angle. So these both the cycloalkane and cyclobutane will have a deviation in the bond angle, and the deviation in the bond angle causes the strain in the angle of the ring. So here the ring strain will make them unstable. So here the ring strain will make them unstable as compared to molecules having tetrahedral bond angle. So these normal tetrahedral angles will produce strain in the ring, and this ring strain will make them unstable, and there is higher will make them unstable as compared to molecule having bond angle. So the molecules which are having the tetrahedral bond angle, they compared to them, these cyclopropane and cyclobutane will have the instability, or they will due to the ring strain in their bond angle. So here so cyclopropane and cyclobutane will easily undergo ring opening reaction to form more stable open chain compound. So in this case, if there is a ring strain is much more, then they will open into a when they are reacted with some reaction, where they are reacted with some reagent, or if they are undergoing any reaction, then they will open at once, means they will form a more stable open chair compound. So these assumptions that are given by the Beers in his angle strain theory, that are helpful in understanding the instability of your cycloalkane ring system. And if the ring in case of your cyclopropane, this ring is in case of cyclopropane, the ring is your triangle. So in the triangle, all the angles are 60-degree angle, and in place of your 109.5-degree angle. So that will cause to adjust them into a triangle ring system. In the same manner, there is cyclobutane, which is having a 90-degree angle as compared to in place of your 109.5-degree angle, to adjust them into a square-like ring system. So the deviation in this cyclopropane and the cyclobutane ring system, then the normal tetrahedral ring, that will cause a strain in the ring. So if this strain will occur in the ring, then this ring system strain will make the unstable as compared to the molecule having tetrahedral bond angle. So cyclopropane and cyclobutane, when they undergo any reaction, any ring opening reaction, then they form more stable open chain compounds. So they are forming a more stable open chain compounds when they are undergoing a ring opening reaction. Then this cyclopropane and cyclobutane will form a more stable open chain compound. The next is your, now compare the stability of cyclopropane and cyclobutane. So if we are comparing the stability of this cyclopropane and cyclobutane, then the bond angle in cyclopropane is your 60-degree, and the normal tetrahedral bond angle value is your 109.5 degree. So the deviation is your normal tetrahedral bond angle minus actual bond angle. So the deviation is 109.5 degree minus 16 equals to 49.5 degree. So the bond angle in cyclobutane is 90 degrees. So in this case, in the case of your cyclobutane, the bond angle is your 90 degree. So the normal tetrahedral bond angle value is 109.5 degree. That is why the deviation equals to normal tetrahedral bond angle minus your actual bond angle. So the deviation equals to 109.5 degree minus 90 degree equals to 19.5 degree. So the deviation for cyclopropane, so the deviation for cyclopropane is 49.5 degree, and the deviation for cyclobutane is 19.5 degree. So the deviation is higher for cyclopropane than cyclobutane. Therefore, cyclopropane is more prone to undergo ring opening reaction. So as a result of this, the strain is more. As a result of this, the strain the strain is more in cyclopropane as compared to cyclobutane, it will make cyclopropane less stable than cyclobutane. So cyclopropane easily undergo ring opening reaction as compared to cyclobutane. Because the deviation between this cyclopropane and cyclobutane, in case of cyclopropane, it is having a higher deviation, that is your 49.5 degree, and in case of cyclobutane, that is the deviation is 19.5 degree. So the cyclopropanes are more prone to undergo ring opening reaction. So they will readily undergo ring opening reactions, and as a result of this, the strain is more in cyclopropane as compared to cyclobutane. So it will make cyclopropane less stable than cyclobutane. So this strain will make cyclopropane less stable than the cyclobutane. So cyclopropane easily undergoing opening reaction as compared to cyclobutane, because there is a less deviation as in cyclobutane as compared to the cyclopropane. So cyclopropane is having a more deviation, so that is why they are more prone to the ring opening reaction. Next is your, according to Bayer, the relative order of stability for some common cycloalkane is as follows. So the cyclopentane are more stable than the cyclobutane, and less stable are your cyclopropane. So the angle strain in cyclopropane. So here you can see that the angle is 60 degree. So deviation is 49.5 degree. So here the band bond, non-linear overlapping. Here you can see the non-linear overlapping. So here between this there is a 115 degree, and between this carbon there is 60 degree angle. So limitations of Bayer strain theory. So what are the limitations for this Bayer strain theory? So in case of this, you can see here that in there is 24 degree 44 angle strain is this much, and in case of this cyclobutane, the angle strain is only 19.5 degree. So the limitations of Bayer strain theory is that the successfulness of Bayer angle strain theory, that Bayer rightly proposed that cyclopropane and cyclobutane are flat molecules and having angle of 60 and 90 degrees. Those are much deviated from the ideal tetrahedral value of 109.5 degree. Hence, these ring systems are unstable and easily undergo ring opening reaction. And there is much angle strain in cyclopropane and cyclobutane. And this Bayer also proposed that the cyclopentane is not need to be planar, but it is a planar, as in that condition the angle is much nearer to the ideal tetrahedral angle. So it also proposed that the cyclopentane is not needed to be planar, but it is a planar, because as in that condition the angle is much nearer, because the cyclopentane does not need to be planar, but it is a planar. So due to this planar condition, its angle is much more nearer to the tetrahedral ring, that is a normal ideal ring bond angle. So the unsuccessfulness of Bayer's angle strain theory. The Bayer's was not able to explain the effect of angle strain in larger ring system, and he, according to Bayer, cyclopentane should be much stable than cyclohexane, but practically it is reversed. It is not stable, but the cyclohexane is stable. So larger ring system are not possible according to Bayer's, as they have negative strain, but they exist and much stable. So the larger ring system are not planar but pucker to eliminate angle strain. So these larger ring systems are not possible according to Bayer, as they have negative strain, but they exist and much stable. But according to the Bayer, that they are having, the larger ring systems are having the negative strain, but the larger ring systems exist and they are having the more stability, much more stability, and they are not planar. These larger ring systems are not planar, but they are puckered, so they can eliminate the angle strain. Next is the orbital picture of your angle strain. So in this, as we know that the bond formation effective atomic orbital overlap is required. So a carbon atom in a molecule, if it is a sp3 hybridized, then the bond angle is 109.5 degree and orbital overlap is maximum. This is the reason for higher stable compound. For an open chain compound, when carbon is connected to other two carbon atom, it is sp3 hybridized and uh, utilizes these hybrid orbitals to form the bond. So in case of your cyclopropane, the bond angle is 60 degree instead of your 109.5 degree. And the carbon atom does not don't use sp3 hybridized to form the bond. So hence the bond is weaker as compared to usual carbon-carbon bond. So here you can see the two type of bond overlapping, that is your good overlapping or strong bond, and the second is your poor overlapping weak bond. So here you can see the band bond in cyclopropane, and in case of band bonding in cyclopropane. So the atomic orbital overlapping cyclopropane. So here next is your band bonding in cyclopropane. So this is the band bonding in case of cyclopropane, and this is less than optimal orbital overlap due to the band bond, and this is the carbon frame of cyclopropane. Now it's the Coulson-Moffatt model. So in the Coulson-Moffatt model, the band bond, that is one of the first band bond theory for cyclopropane, was a so-called Coulson-Moffatt model. So this is the band model, or you can say the banana model. So banana bond. So this Coulson-Moffatt model is also known as band bond or the banana bond. So this band bond, one of the first band bond theory for cyclopropane, and they are so-called Coulson-Moffatt model. And a band bond is also known as banana bond. So this is also known as banana bond, and it is a type of covalent chemical bond with a geometry somewhat reminiscent of a banana. So it this band bond, which is also known as your banana bond, it is a type of your covalent chemical bonding, and it is having a geometry that is somewhat reminiscent of a banana. So as you can see, this banding of this bonds. So here the term itself is a general representation of electron density or configuration resembling a similar band structure within small ring molecules such as cyclopropane, as a representation of double or triple bond within a compound that is an alternative to a sigma and pi bond model. So this term that is this term that is your bent bond or the banana bond, it is a general representation of electron density or configuration resembling a similar band structure with the smaller ring molecules. So it is a representation. This is the banana bond, as you can see here. This is the banana bond, and this is the atomic orbital overlapping cyclopropane. So this shows a similar as a banana bond. So that is why it is known as your banana bond. So in this case, the term that is used here, that the band bond or the banana bond, that is a general representation of electron density. So it is showing here electron density or a configuration that is resembling a similar bond, that is resembling a similar bond with a small ring molecule such as your cyclopropane. So here this is your cyclopropane, which is showing a representation. This is showing a configuration resembling a similar band structure within a smaller ring molecule, and such as your cyclopropane, and so which is a cycloalkane. And here this is shown by this Gaussian-Moffatt model, was showing the band bond theory in the cyclopropane. So this model is showing the theories of band theories in your cyclopropane, and this cyclopropane, that is an alternative to the sigma and the pi bond. Means here this band model is shown in the cyclopropane, or it is shown in the, it is a representation of double or triple bond within a compound, and this is an alternative to sigma and the pi bond. So this is the Coulson-Moffatt model. This is known as band bond or the banana bond, and in this band bond, one of the first band bond theory for cycloalkane was so-called Coulson-Moffatt model. So the first band model theory is on the cyclopropane. So the theory that was first proposed on this cyclopropane, and it is called as Coulson-Moffett model. And in this, the band bond is also known as your banana bond. If this band bond is known as banana bond also, as you can see here in this structure, this banana bond is also showing the same this band bond, showing this band bond. So that is why it is known as your banana bond. And in this banana bond, it is a type of covalent chemical bond. So covalent chemical bond with a geometry somewhat reminiscent of a banana. So this band bond is showing a type of your chemical covalent chemical bond, and the term itself is a general representation. So this term, this band bond term is representing the electron density, or it is showing the configuration which is resembling the similar band structure within a smaller ring molecule. And the smaller ring molecule is your cyclopropane, that is your C3H6, or they are represented this showing this configuration, or these are representing the double or the triple bond within a compound, and it is representing, it is that is an alternative to the sigma and the pi bond model. So these are the atomic orbital overlapping in the cyclopropane, and this is showing the banana bond, and this is the bent bond in cyclopropane. So what is this band bond? So ये band bond what क्या है? So sigma bond have head-on or end-to-end overlapping. The hybrid orbital, including the intersection bonding region, are present equally on both sides of the molecular axis. But in case of pi bond, the lateral or sidewise overlapping of p orbital occurs, and here the bonding intersection area is totally out of the molecular axis. So here, what is the band bond? So the sigma bond, as you can see, the sigma bond. This is your sigma bond. So sigma bond have head-on, or the end-to-end opening. So here the end-to-end overlapping. Here you can say that this is the head-on or the end-to-end overlapping, and the hybrid orbital, including the intersection. The hybrid orbital, which are including the intersection bonding region, are present equally on both sides of the molecular axis. So these intersection bonding regions, these are present equally on both sides of the molecular axis. So here you can see this is the molecular axis, and this hybrid orbital, including the transaction, here you can see transaction bonding region are present equally, like both sides are equally and on both sides of the molecular axis. So in this side also, this is having the same bonding region, and this is also having the same bonding region. So here, but in case of pi bond, the lateral or the sidewise overlapping of p orbital occurs, and hence the bonding intersection area is totally out of the molecular axis. But in case of your sigma bonding, the hybrid orbital, that is the intersection bonding region, are presented equally on both sides. But in case of your sigma bond, which is caused by the sidewise overlapping, here you can say the sidewise overlapping of p orbital. So the bonding intersection area is totally out of the molecular axis. So this is out of this molecular axis. Next, in the bent bond, usually they are sigma bond. So in the band bond, they are usually sigma bond, and the hybrid orbitals and the intersection bonding area are not present equally on both sides of the molecular axis, and the bonds are bent towards the direction of angle strain. So they are somewhat more unstable than sigma bond and less unstable than pi bond. So these band bond, they are usually they are the sigma bond. The band bonds are usually known as the sigma bonds, and the hybrid orbitals and the intersection bonding angle area. So the hybrid orbitals that are formed, or the intersection where the both the bonds are overlapping, so that area are not present equally on both sides of the molecular axis. So the bonds are bent towards the direction of, so the bonds are bent towards the direction of angle strain. So they are somewhat more stable. So they are somewhat more unstable than the sigma bond, and they are less unstable than the pi bond. Next is your question and answer questions. So according to the Bayer strain theory, which is highly stable, that is your B, that is a cyclopentane, that is highly stable. Identify the incorrect statement regarding cycloalkanes. Alkenes. The bond in them are fewer compared to those in alkenes. They occur in gaseous form in nature. They undergo polymerization. The conjugated double bond in them increases their stability. That is, they occur in gaseous form in nature. Next, identify the incorrect statement regarding cyclobutane. So, cyclobutane is a commercially important compound. Identify the compound with the highest ring strain, that is your cyclomethane. Which amongst the following compound explodes on contact with oxygen, that is a cyclopropane. So cycloalkanes have the same melting and boiling points as their corresponding alkanes. No, false. These are the references from where you can study this topic, this cycloalkanes theories. And thank you so much for today's lecture.